begin by thanking the organizers, but in particular, the organizers of the conference, Tom, G, Lara, and Rajesh, but also all of them for putting together with me this wonderful program. I very much enjoyed myself and enjoyed interacting with them and crafting the program, so thanks for a great few months. So indeed, I'll be talking a little bit about superstring partition functions in AdS3, and this is work ongoing with Christian Ferko, who is our postdoc, and Samir Murthy. And the question we're going to discuss, and you'll see what's new and what's been done before as we go along, began about a year ago when I was here and chatting with Samir at the Bootstrap conference last year at KITP. We were asking the following question. One of the lessons we've learned in the last few years is near extremal black holes, especially non-supersymmetric ones, are not as complicated as one might have thought they were from classical general relativity and semi-classical physics. They don't have a non-trivial degeneracy once one includes quantum corrections. It's a lesson that we learned from the initial work of Ghosh, Maxfield, and Turiachi, and more concretely laid out in this beautiful paper of Iliescu and Turiachi. The main point there in these discussions is that if you look at the semi-classical fluctuations, it's not enough to compute the saddle point action, but you also need to compute the one-loop determinant, and the one-loop determinant is dominated by a soft mode, and the soft mode dynamics suppresses the near extremal entropy. All of these calculations to date have been carried out in the semi-classical regime, where you just have some gravitational theory and fluctuations thereabout. But this effect of the zero modes contributing to the one-loop determinant should be a robust prediction of any theory of quantum gravity. So one might ask, should this not be true in string theory, and how would it work if we account for finite string length? Okay, so that was the question we started with. And I'm going to contextualize that question. I'm not going to try to answer it in detail. I'm going to give you a particular example. But thinking about that particular example led us to a series of interesting puzzles, or perhaps rabbit holes, but you'll see as we go along. So with that motivation, let me talk about AdS3. And I'm going to frame the question slightly differently, but I'll come back to what I just said in a moment. So the spectrum of strings modes in AdS3 should contain a set of boundary gravitons associated with the Brown-Hanno large diffeomorphisms. These modes are clearly visible if you do semi-classical fluctuations around AdS. This was first pointed out by Maloney and Witten and beautifully computed in the one-loop determinant heat kernel calculation of Simone, G, and Alex. We can also infer that these modes exist from the worldsheet analysis given on Kutazov-Seiberg in a very early paper on the subject, constructed vertex operators that would generate the boundary Virasoro algebra. So I could reframe my question, and this is a related question. Where are these modes in the string partition function? Okay. If you ask the question in the context of superstrings, you should see a boundary supergraviton multiplet, and more importantly, small addition on top of that, you should also see the supergravity fluctuations, the chiral primary states. If you then take this result and use the following observation that goes back to these people, in a 2D CFT with a twist cap, there's a nice universal limit that reproduces this Schwartzian contribution. Okay? So as long as the string length is finite and you're away from a tensionless limit, it follows that the statement I asked in the question I asked in the previous slide has an affirmative answer, namely that the entropy of near extremal BPS black holes would near extremal BTZ black holes would indeed be captured by this universal answer. So you get the Schwartzian correction and you'd get the suppression of the near extremal entropy. Okay, so and once we have this superstring partition function, we could do all sorts of tests, and we can do, while we can do those things, trying to just go through this analysis over the last few months led us into a bunch of interesting surprises and subtleties. So I'll sort of explain some of those things in some depth. Okay, but to warm up, let's just talk about the bosonic string, and then proceed to the superstring in a bit. So to set the stage, I'm going to look at something very simple. Let's just look at a string propagating on AdS3 and some internal space X. I'm going to assume nothing about it for now. And it's going to be, this solution is going to be supported by pure NS flux, and this renders the part of the AdS3 geometry solvable as an SL2 WCW model with level K, where K is the string length, where A is the AdS length in string units. Okay? And all I'm going to assume about X is that it's a unitary CFT with some appropriate central charge to make a critical string. I'll take K bigger than 3 for most part, even though smaller values of K are allowed, because at K equals 3, as Matthias, Rajesh, and Chris Hull showed a few years ago, there is a infinite higher spin, there's a tower of higher spin states that starts from the continuum. What we'll do is we'll try to compute the string partition function in thermal AdS3. So I'll take AdS3 in some Euclidean AdS3 in some standard coordinates, identify time, make time compact, and also turn on a chemical potential for the angular rotations. Okay. So our expectation is this partition function should capture the contribution from boundary gravitons, the matter states that are there in this XCFT, and also the stringy oscillators. So that's what we should expect. Okay, so that's for orientation purposes, there are going to be many tori and many modular parameters. So let me just give you my notation. So there's a worldsheet torus. I'm going to try to compute a worldsheet torus partition function. And contrast to usual, I'm going to use T to denote its modular parameter and Z to denote the exponential of the modular parameter. The AdS3, as I said, is in Euclidean signature. I have identified time and I've introduced a twist along the angle. So that has a boundary torus whose modular parameter, I'll use the CFT language and call that tau and its exponential q. Okay. So as I said, we just want to compute the one loop determinant of string fluctuations, and that's going to be computed by this torus partition function. Okay. Note that this worldsheet torus is winding around the space-time time circle. So there's a momentum and winding modes. I'll just work in a convention where both of them are winding modes, so there'll be two integers characterizing my solution. Okay, so we need the worldsheet partition function. That's going to be given by the integral over the worldsheet modular parameter, the fundamental domain. There's a piece of the worldsheet partition function which comes from SL2, the AdS3 part. There's a piece that comes from X, and there's a piece that comes from this BC goes. The X part I won't say anything about for now, because later on I'll talk about a superstring. I'll specify it a particular internal space, and we'll see some structure there. We'll just assume that it has a standard Taylor expansion in the e to the 2 pi it. And the SL2 part was worked out in a very beautiful paper nearly 25 years ago by Malasena, Uguri, and so on. And here's the answer. I'll unpack this for you a little bit. So it has a contribution here from the winding states. This is the same answer you'd have if you have a circle in flat space and you're computing the compact boson partition function. The denominator, if it was 3 non-compact directions, you'd have just a compact boson partition function in eta cubed. But that eta cubed has gotten deformed to a theta function, a Jacobi theta function, because there are the directions of AdS, which are perpendicular to time, are twisted with respect to the winding, so they are charged and they pick up a worldsheet holonomy, which is this UN. Okay? And in addition, the fact that AdS3 is non-compact reflects itself in this 1 over square root T2 that's sitting out there, which is just a non-compact boson part, the partition function. As I said, this answer is well known. What we're going to do is try to unpack this and try to extract what this worldsheet, what it says for the space-time CFT. I'll emphasize for the moment that the contribution, all I'm going to try to compute is the one loop determinant around a single geometry, namely thermal AdS. It's not by itself likely to give a space-time modular invariant partition function for the dual CFT. Okay. It, however, will suffice to extract asymptotics, just as the case with the thermal graviton partition sum. Okay. So what we expect is that there's a piece of the CFT partition function, which will be the tree-level answer, which is the Bekenstein-Hawking-like entropy, which I'm going to say nothing about for now. And then there is the exponential of this worldsheet partition function, which is the one-loop contribution, and we're just going to try to extract this piece. Okay? So is the setup clear? Great. So what we need to do is to actually do the integral over this modular worldsheet modular parameter. And there's a standard trick for this. This is a trick that was introduced by Polchinski a long time ago, that you use the fact that the worldsheet integrand is modular invariant and unpack the integration domain from this fundamental domain to the entire half strip, trading this double sum over two windings for a single sum over one of the windings. So think of it as just a winding around the thermal circle, and drop the part that comes from the zero modes. This answer then just, which goes into the exponent, looks like the sum of contributions from multi-wound strings. So you should think of this for given M as the M string contribution to the partition free energy, to the space-time free energy or the worldsheet partition function. If I just, so I'll just look at one term here, and then I can do the sum post facto. Okay, so that's the single string free energy. And the single string free energy, I have rewritten it following this paper I mentioned by Balnasena, Oguri, and so on, and introduce an auxiliary parameter to simplify some of the integration. So I have the integral over the tau1 and T1 and T2 for the worldsheet moduli, and then I have some auxiliary parameter that was just introduced to Fourier decompose some pieces of the partition function. The rest, the Z partition function, the Gauss and the SL2 part, basically now are just some infinite products, and you see both the presence of the Q from the space-time and Z from the worldsheet. Okay? And AK here is just a 0-point energy. This is a bosonic string, so there's some non-trivial 0-point energy which is going to lead to a tachyon, so I'll keep that floating around in what follows.
I mean, normally expect something like relation from a single particle free energy to the Bose free energy to have some 1 over m sort of symmetry factor.
It's in the beta, so M is Q is e to the m beta. So when you do this, I haven't. When you put multiply m here and put the 1 over m, it's hidden in my notation. It's there. It's there. Otherwise, it's not the correct Bose statistics. Thank you. Okay, let me say a few words about what the spectrum is, just before I actually do the integral and rearrange it a little bit. So before, in a previous paper, Balnasena and Oguri actually worked out the spectrum of strings by canonical quantization, and they had a specific proposal. They said that the states of the string fall into two sets of representations of SL2, the discrete series and the continuous series. And in particular, unlike usual compact WCW models, spectral flow here generates new states. So the states are labeled by the oscillator excitations in AdS, in the SL2 part, the dimensions of operators of this XCFT, and a label that corresponds to how many integer units of spectral flow you do in this theory. Okay? So if you look at the spectrum, the CFT, I'm just intentionally writing the spectrum in terms of CFT parameters, the space-time CFT parameters. So you see there's some states whose energy scale like square root k. These are the stringy oscillator states. And then there are additional states from the continuum whose energy scale like k. Okay? So if nothing I've said so far, I have made no assumptions about what k was. K could be anything. I just wanted it to be bigger than 3. So I could be either in the semi-classical regime or I could be in the stringy regime. In the semi-classical regime, states with non-trivial k dependence will of course be heavy. They'll be coming from stringy oscillators or from these continuum series. Okay? Good. We can do the integral. Okay? So this is not new. This was done already in this paper. We're just going to rearrange their answer. So the integrand is tricky, but these folks carefully argued how to actually do the integral, and I can explain that to anyone who wants to know afterwards. And I'm going to organize the single string free energy into 3 pieces. It's a bosonic string, so there's a tachyon, which I'm just going to not talk about. There's the piece coming from these discrete series representations, and there's the piece coming from the continuous series representation. If I take the answer and do the integral and write out the discrete series representations, turns out for generic x, in particular for x CFT that does not have any conserved charges, the answer takes the following form. There's some piece here which doesn't scale with k, and there's a piece here which starts with square root k. Okay? So if you think about what this means, all these states look like you get q to the h, q bar to the h bar divided by 1 minus q mod squared. So these look like basically representations of a Virasoro algebra, which when you sum over this M and compute the multi-particle answer, naturally organize themselves into the answer you expect for particles propagating in AdS. Okay, so this is exactly like the heat kernel calculation that you would do in semi-classical gravity. What's interesting are these 2 pieces. These are purely holomorphic or anti-holomorphic, and they are at the lowest line level. And if you multi-particle them, so like if you forget anything from this talk, one word I would like you to remember is the word multi-particle. It means summing over the free string Fock space or free particle Fock space to get the Bose statistics appropriately sign corrected for me statistics answer. Okay, the one loop partition function reproduces exactly what you expect from the boundary gravitons. So indeed, the boundary gravitons are in this partition function. They just needed to be exposed, and once you rewrite this partition function in an appropriate way, you get the contribution from it. So once you have this, and you realize that for any k, these states are gapped relative to these currents, and for generic x, these are the only currents that you have, we can immediately apply the result from Henry, Joaquin, and Annemiek's paper and recover the prediction for the for non-supersymmetric BTC partition thermodynamics. The string answer would give you a t to the 3/2. It would give you this asymptotic Cardy-like formula corrected for this high spin, low temperature answer. So it works for any k bigger than 3. We didn't have to use semi-classical gravity. It's a bit of a heavy hammer to get this answer, but we have the hammer so we can compute it. Okay? Yeah? No, it's there, and we just chose not to talk about it in this discussion. So because what I really want to do is talk about a superstring. So in that case, there's no tachyon, so we don't have to worry about it. Any other questions? Okay, great. Yeah, of course.
Is there a role for higher alpha corrections in the underlying geometry, to the underlying geometry? Before you get into levels of that, any role for that?
We have an exact worldsheet CFT for any alpha, for any k.
Okay.
So we don't need to correct the geometry. Yeah, I mean, of course, that's part of the simplicity of this example, which we had a solvable WCW model to begin with.
So are you saying that the string theory isn't making a difference to the resolution of the standard universality?
Yeah, because the point is that it's going to introduce stringy states, but they're going to have alpha prime effects. The only thing that can spoil it is if the twist gap closes, but the twist gap doesn't close for generic alpha prime. Yeah?
But your motivation was the stringy effects as opposed to other effects, right? So
But I'm saying that this answer is true at finite string length. Yeah. It's not surprising, but it's just verification of a non-surprising fact. Okay, so let me move to the superstring. So I'll focus on type 2b, on AdS 3 times S 3 times T4. And will work in this case. The worldsheet theory, again, is with NS and S fluxes, is solvable. It has a super WCW model for the AdS3 part and a super WCW model for S3, and we'll just take 4 free bosons and fermions for the T4. Okay. In fact, you can more or less reduce this to well-known facts using a known result about n equals 1 WCW models, that you can decouple the fermions and just write the bosonic WCW models with shifted levels. So the SL2 and SU2 would have started out as super WCW models with levels k, but with the shift, the SL2 gets upshifted by 2 and the SU2 gets downshifted by 2. And you just have free bosons and free fermions. These free bosons are for the T4, and the free fermions, there are 10 of them from all of these guys. If you work on the dual spacetime CFT, it will have 4,4 superconformal symmetry. And what we aim to recover is, as we'll see in a minute, I have intentionally used the word perturbative. We'll aim to recover the perturbative part of the vacuum character, because the vacuum character with 4,4 supersymmetry is a bit more complicated than the Virasoro vacuum character. We'll also turn on some chemical potentials for the rotations along the S3 so that we can track which representation states fall in. Okay, so my picture is that I've just, as before, I have AdS3, I have an S3 written in some flight coordinates, and I'm going to twist as I go around the time circle, not just the angle in AdS3, but also the angles in the S3. Okay, so I'll use rho for the complexified chemical potential in S3. And so what I'm going to have is a partition function, which will have 2 pieces, contribution from the bosons, contribution from fermions, and still winding sums from both the sets of windings around the circles, the thermocircle. Okay, let's take this piece by piece. So the bosonic piece is already a bit more complicated. So the last 2 pieces are the free bosons of the torus and the BC ghosts. The first piece is the same answer as SL2 with level shifted by 2. So it's not new result. And the middle piece is the SU2 partition function, the A series modular invariant that you can just write down using algebraic stuff. Okay? But because of the twist, note that everybody has twisted labels everywhere. There's a FNM which I'm not going to talk about. Ask me later what this prefactor is. It's there to sort of make this modular invariant. The fermions, you have a choice. You can either make the fermions periodic around the time circle in spacetime or anti-periodic. Should you make them periodic and do the standard GSO projection and spin sum, you get some answer which is some product of theta functions divided by eta. Or where this combination B and M that shows up here, this twist, is a combination of the twist from the AdS3 part and the S3 part. So it's a bit more complicated than, whereas the bosons don't see each other, but the fermions talk to each other because of GSO projection, that they get sort of mixed up. Or you can do anti-periodic fermions. The speed sub now has to use the Attic-Witten phases, and you have a slightly more complicated answer. Okay, so you have 2 choices to make. Again, we're not the first to write this down. This was written down by various people, including Subrat, who has studied this a long time ago. And more recently, Dabolkar and Moitra used this latter result to say something about entanglement entropy in AdS3. Okay, the reason I turned on these chemical potentials was in the CFT language, I want to be able to talk about the CFT partition function as a function of the CFT modulus Q and chemical potential R. And what I will think of is either computing trace in the NS sector of the space-time CFT of Q to the L naught Q R to the J, or by shifting this chemical potential by 1 unit, considering the trace with -1 to the F inserted. Okay? So this trick that we've learned to use exploit very well by turning on angular momentum to chemical potentials to write down -1 to the F. Since I'll talk about the NS sector states, they're characterized by their conformal weights and arc charges. So the states in the dual CFT will have 4 labels, their conformal, the left and right conformal dimensions and their R symmetry labels. And the BPS bound says that the left and right conformal dimensions are bounded from below in the NH sector by their R symmetry charge. Okay, again, in theory it's not hard to do. You can do it using the same tricks. And I'll now package this answer in 3 pieces. What I'll call the supergravity piece, the string piece, and then the continuum that exists because of the non-compactness of AdS3. The supergravity piece turns out to be remarkably simple. Okay? So it looks like there's some piece here which I'll unpack in a second, and it just has contributions from various spins. This is coming from the SU2 part of the partition function, from spin running from 0 to some upper bounded by something of order k over 2. Okay? And I've written this answer, and I'm going to keep writing this answer in suggestive ways to show you at the end of the day how to organize the spectrum directly into n equals 4 characters without doing too much work. So I've written the answer already in terms of spin j characters, so you can see that SU2 spin half character, SU2 spin 1 character, and so on. But we can do something bit more. The n equals 4 algebra has a global SU11/2 part. And the short multiplets of this have a very simple character representation. So the spin j representation has one particle of spin j fields with weight j because of the BPS bound. It has q action on it will give you spin j minus half fields with weight j plus half, and q squared action will give you spin j minus 1 fields with weight j plus 1. So I've just packaged everything. So bold-faced chi with subscript j will represent SU11/2 characters, whereas unbold-faced chi will represent SU2 characters.
But j equals to half, the last one isn't there, right?
J equals half? I mean, yeah, so when j gets low, you get truncated out. When this gets negative, you throw them away. So that's why when you write chi half only gets these 2 contributions. It does not have the last piece. Thank you. Okay. One more comment before I actually complete that result and tell you what it shows for the field theory. So if you write down the full character for the 4,4 algebra, which was done a long time ago by these folks, it has theta functions coming from the fact that there are 4 fermionic generators. So that's the theta function in the numerator. Actually, that theta function divided by eta squared is that fermionic superconformal part of the superconformal generators of this n equals 4 algebra. The eta piece knows about the Virasoro generators. And then this theta function here is because this algebra has an SU2 R symmetry. So that's the SU2 character. However, because this module, including the vacuum module here, are not freely generated. There are lots of null states simply because SU2 characters have null states. And this sum here is the sum that is the alternating sum that projects out these null states. Okay? And that's the answer that's here. In fact, if you take this character and take j to 0, you will see that this combination, one piece of that combination will give you 1 minus q to take out the L minus 1 from the eta. Okay? But note that the null states have dimensions of order c, where c is a space-time CFT central charge. This guy is not perturbative from the point of view of the worldsheet. The worldsheet knows about AdS length scale in string units, which is k. This C knows about AdS length scale in Planck units. And there's a difference, which is P, which is the number of, which roughly speaking is the number of fundamental strings in this background. K is roughly the number of D-branes, and that piece is missing. So if we want to reproduce this character, we can't do this by looking at fluctuations around a single geometry. This, of course, is well known, and this was well appreciated, as you'll see in a moment, from calculations that were done a few years ago by Luca, Joaquin, and friends in the context of super JT. They had to sum over saddles. All terms, apart from the m equals 0 term here, are non-perturbative from the point of view of the worldsheet calculation that we're doing. So we'll take one baby step, we'll try to get the m equals 0 term and then see how we can complete it and what we can do post facto. Okay. So I'm rewriting here the supergravity part of the single string free energy. If I just pick out the spin 0 part, there's a purely holomorphic piece and a purely anti-holomorphic piece, okay, which are again written in terms of these SU11/2 characters. This piece, if you multi-particle, you will reproduce the expression I showed you on the previous slide, in fact, the m equals 0 term. Okay, so it knows about the boundary supergravitons. The second piece, if you multi-particle, knows about 4 free bosons and fermions, which are the 4 currents that are coming from the torus. Okay, so indeed, so one reproduces precisely the expected answer for the supergraviton multiplets. And you can think of this as the most heavy-handed way of doing what Alex, G, and Simone did to compute the n equals 4 character by doing the string theory calculation or the supergravity calculation. Okay? So this calculation, as far as I know, in supergravity is not in the literature. Various people have done it in private notes, as Joaquin told me, and some of us are playing with it here. But as I pointed out a moment ago, Luca, Joaquin, Matt, and Wen Li Zhao worked this out in the context of super JT. Of course, it reproduces the same answer, and they used it to talk about BPS black holes. Okay. I should point out that there are only 4 free U1 currents and their super partners on the left and on the right. There aren't 8. There's been an expectation going back a couple of decades that there might be 4 more additional U1s coming from Ramond fields. We only see the U1s coming from the NS fields. I've talked to various people about this. I don't think the partition function knows about the currents coming from the Ramonds. Okay, so now let me quickly in the next couple of minutes finish up by telling you how to fill up the rest of the supergravity spectrum. At this point, I gave you a formula. It's a very simple Klebs-Gordon analysis for SU2. Just put together the SU2 Klebs-Gordons, and you'll find that the pieces for j equals 0, the pieces that was not just purely holomorphic or anti-holomorphic, completes to this, and this guy completes to this, where these combinations are just left and right combinations of SU11/2 characters. And you can eyeball this from the calculations that were done in the 90s by these folks to check that you reproduce on the nose the expected answer from supergravity. Of course, this is not a surprise. Already way back then, these folks had argued that the canonical quantization of the string reproduces the chiral primary spectrum from supergravity. It was also worked out nicely in these papers following. Okay? Looks great. And we could take this answer, add one more piece, namely the m equals -1 term, and use that to compute the near extremal BTZ thermodynamics by doing, as was done in the case of super JT. So I won't go through that detail. And to do that, you need to also know what the saddle point answer is, what the non-perturbative piece of the answer is, but that you can sort of start to guess using this recent result of the Casimir energy by Lorentz and Stridi. Again, all I want to say here is that the string calculation with these assumptions verifies our expectation that result holds not just in supergravity, but all the way at finite alpha prime. Okay. At k equals 1, of course, it won't work because there's a higher enhanced higher spin symmetry, as these folks showed, and Jake talked about this on Tuesday. Now, we should be able to do this for other backgrounds. Okay, I just to pick T4 as an example. We should be able to do K3. We should be able to do S3 times S3 times S1, etc., etc. In particular, if I started with 2A on K3, then it should be dual to heterotic on T4, and that doesn't have supersymmetry on one side. Okay. And here we run into a puzzle. So we tried something naive. We tried to compute the K3 partition function by taking the Z2 orbifold of T4. And we expected that we should retain the n equals 4 generators, but project out the U1 currents and their super partners. That's exactly what K3 projection should do at the level of supergravity. what we find is something funny. We find we project out half of the spin 3/2 generators of the superconformal algebra and half of the fermions. This is not right. It says something about our identification of -1 to the f worldsheet. But when fixed, they should give you, there should be two independent constructions of chiral GSO projections that give you the type 2a and the type 2b theory, one with 4,4 and the other with 4,0 supersymmetry. Okay, so this is a puzzle that we have not solved. We've been sort of thinking about it for a while now. Let me end with final comments. I motivated this discussion by saying, we would like to sort of see the dynamics of the Schwartzian from the string. But, one thing that's unsatisfying about this is that the Schwartzian lives in the near horizon region, lives at the throat where the near horizon joins to the asymptotic region. Wouldn't it be lovely if you could find a collective mode that lives in the entire space-time, contributes to the one-loop determinant, exactly the same way the Schwartzian does? Sort of clean up some of these discussions and be able to do calculations in various asymptotics. Okay, so fresh off the press, something that we more or less converged on yesterday with Maciej Kolonowski, who's mostly been driving this with Don Marolf, Joaquin, and my student Ilya Rakic, is that we seem to have found a set of eigenfunctions of the spin 2 Lichtenowitz operator around the near extremal BTZ black hole, which are almost zero modes, and therefore give the same contribution to the determinant as the Schwartzian, but without ever talking about the near horizon region. This is the entire AdS3 keeping the asymptotics. Okay? So of course, one would love to know what is their signature, they're slightly off shell modes, how would they look like from a worldsheet point of view, and other questions of this kind. Okay, with that, let me end, and thank you.
Very much. Questions?
Thanks for the lovely talk. In 4,4 AdS3 supergravity, I think we did do an analysis of the partition function. But anyway.
I meant a heat kernel calculation.
Oh, yeah, we didn't do a heat kernel calculation.
That's all.
Yeah, we did a boundary graviton calculation.
Yes. That's
other question is, you've derived some, leading properties of the statistics of microstates from the superstring.
Yes.
Can you hope to derive more about the statistics of microstates, like higher point functions and properties like chaos from the worldsheet perspective?
That would be very nice. Ideally, one would like to sort of do the calculation that Steve and Douglas did, for example, directly from a worldsheet. Not there yet, but it's something that's definitely worth thinking about.
I guess my question is, where did you make an approximation, or what approximation drops the higher terms in the statistics?
Well, we are only computing the torus partition function, right? So it doesn't know anything about some of the other statistics that you're asking. Yeah.
So which specific string modes contribute to the partition function the same as the Schwartzian contribution?
So if you want to track the Schwartzian contribution, one of the reasons I sort of talked about boundary gravitons. If you go through the mechanics of how the result was derived originally from the 2D CFT language, all you really care about is that you have the vacuum character, and then every other state there's a twist cap to every other state in the spectrum. So I'm computing the partition function around thermal areas. To get to the BTZ, you have to do an S modular transform. If you just take the vacuum character and do the S modular transform, and take the appropriate limit, you'll immediately get the answer. So the part I really need from the string is to be convinced that the string knows about the boundary gravitons. So that's all I need. I don't need to know that, and the fact that responded to Eva earlier, I just need to know that everybody else, every other state has a twist gap for finite alpha. Switch it on.
Yeah. I just wanted to make a comment. Can you go back to this slide where you talked about these different spin fields coming from supergravity? Yeah. No.
No, it's the next slide. Okay.
I think it's the one after.
Sorry. I have to wait for it to finish.
Yeah, that's one, I think.
This one. Yeah.
No, it's about the. Never mind. I'll just say. Never mind. I'll just make the comment.
Yeah.
So, a few times you mentioned that this is sort of a very high-tech way of calculating something that, in principle, you could have done using supergravity.
Yes.
But I think it's worth emphasizing that the string calculation gives you a little more, namely, for example, about the question of what are the massless, what are the chiral currents.
Sure.
That, I think, is a consequence of the modular invariance of the string worldsheet, because the supergravity a priori, that's not a priori determined by group theory or supergravity. It's some constraint on the whole spectrum.
I think if you did an honest heat kernel calculation as these guys did, I think you would get it. But maybe we should argue about this offline. Okay. I mean, I take your point. Yes.
Yeah.
Thanks for your talk. So in a context of 2D CFT, so we know all the excited states are suppressed because of the twist gap, and we also know that if you resum everything, then also there is some control. So is it possible to show similar control in this kind of calculation, like all the other states, like even if you sum them up, there are infinite number of stuff, but still they are under control?
Yeah, we've not tried it. I mean, that's one of the reasons I was asking you the other day about just even the n equals 4 character. Because already there, I think it's not super obvious to me, but it's a question that would be worth thinking about carefully. I mean, now we exactly know what to shoot for.
Thanks.
If there are no more further questions, let's thank Mukund.